Hi, good evening, everybody. This is Dr. Roshli from the medical team of USV, and a very warm welcome to all for the SAIL-ESI event, that is AI in Endocrinology, an initiative brought to you by Team ESI in collaboration with the US. After the successful completion of our Module 1 on prompting and literature search, today we have our experts, Dr. Lakhani and Dr. Shahir, who are going to enlighten us on machine learning and Google Teachable Machine. I welcome J Lakhani, consultant endocrinologist, Sidus Hospital, Ahmedabad, founder, Millites Healthcare, and winner of the President Gold Medal in Endocrinology. It's an honor to have you here with us today, sir. I welcome you, and over to you for the further proceedings.
Thank you so much. Good evening, everyone, and welcome to the part two or the module two of the SAIL-ESI program. And we had a fantastic first module where we learned about the basics of prompting, and we also used some of these AI tools for generating content in terms of the literature review. So today we are going to now go into the more difficult spaces. We are going to go into actual how you can use AI for your own research project. So again, if you remember what we said last time, it's basically to spark ideas in your brain, to get insights into how you can use AI for conducting research, especially in the field of endocrinology. So whether you are a first year DM resident and thinking of a thesis project in this field, or you are a senior consultant and looking at furthering your research or using your existing data to generate more data out of it or to generate a machine learning model out of it, that is something which we'll be looking at how you can use it. So what I'm going to do is I'm going to first introduce you a little bit about machine learning, and then we'll go to our guest speaker today, Dr. Shahir. Dr. Shahir is a pulmonologist, but pulmonologist turned AI professional. Well, you'll see quite a few. Last time, Avnish was in a similar board, and this week here, Dr. Shahir, who has become a full-time AI doc, a bit of it, right? That's what we're going to have him. Fantastic teacher. We had a session earlier, and it's going to be great. And he's going to show you Google Teachable Machine. And trust me, if you've not seen Google Teachable Machine earlier, it's going to blow your mind, right? And immediately, the first time you see it, I'm sure there'll be 100 ideas in your brain of how you can use it for AI research, right? From everything from diagnosing diabetic foot ulcers to making a model, the best model possible for retinopathy, or models that will help you diagnose thyroid nodules, classify thyroid nodules, right? It's all there, right? It's just, we'll leave it to your imagination of how you can use it in the best possible way. So that's the whole idea. Now, let me again, some few housekeeping rules for you and just reiterate some of the points. Today's lecture, we'll have a recording of the same, and we'll have some of the presentations on technocrinology.com. So you can go on technocrinology.com and you will be able to access the material over there. So in case you miss parts of it out, you can go there and you can check it out. Additionally, the last lecture, if you had missed it out, you can go there and again see there. The presentations of both mine and Avnish's presentations are also going to be there. So you can just browse through the presentation also and see what you missed. Additionally, we are streaming this on Technocrinology India YouTube channel and other channels as well. Those who are joined from there, welcome, and great to have you as well. That's the housekeeping rules. And again, if you have a question, just put it in the Q&A section of the Zoom webinar. If it does not impede the flow, I'll be a moderator behind the scenes. So if it doesn't impede the flow, we'll try to answer it live. Otherwise, I'll try to answer the thing on behalf of Shahid. And then if there are questions which require you to speak something, we'll allow you to just raise your hand in the end. We'll allow you to speak. And then that point of time, you can come up live and ask the question. So that's the whole flow. So again, starting with machine learning and giving you some practical foundation and hands-on example. So before that, introduction to Dr. Shahir. Dr. Shahir is a DM in pulmonology. So just like a lot of us, he's a polymath, right? You can see constant love for learning. I think that's very clear. A lot of super specialists have that keen interest in a lot of things. Now, presently, he is the lead clinical AI scientist at Anumana AI. He is looking at, so this company is looking to be the leader in AI in cardiology, where he's looking at specializing, conceptualizing, developing, and securing an FDA approval for AI algorithms especially in cardiology, and I'm sure in pulmonology and hopefully in endocrinology also. So he leads a team of doctors and engineers who have developed ECG models to detect pulmonary hypertension, which is right in his field, and low ejection fraction, and multiple models which look at various stages of FDA approval process. He, of course, personally has a lot of patents and has extensively worked and published in leading journals. And again, in future, we would love to have Endocrine Society of India actually collaborating with Dr. Shahir and the company to develop our own innovations in this field. Welcome, Dr. Shahir. From on behalf of the endocrine community, welcome to this session.
Thank you very much, Dr. Lakhani.
Thank you. Before we bring Dr. Shahir to front, we are going to have a little bit of an introduction to machine learning, just to give you an idea of what it is. Machine learning is a subset of artificial intelligence, one subset, which I think endocrinologists will find it very useful. It's basically, just to give you a simple example, it's a predictive system, right? So and that's what in endocrinology, we are, in a sense, predictors of the future, right? We work in a field which is highly dependent on preventive medicine, in a sense, right? We are looking at, let's say you are treating diabetes, you're preventing diabetes related complications, microvascular complications, macrovascular complications. You are also diving into preventive cardiology to a lot of extent, trying to prevent a stroke or a myocardial infarction, trying to prevent or worsen diabetic kidney disease, prevent retinopathy, diabetic foot. So ultimately, what you're doing is you are looking at prevention. And when you have prevention, you require prediction, right? And prediction requires machine learning. So that's one place where it's endocrinologists really have an edge. And that's why we chose machine learning as an important fundamental, which all of us need to learn. So where do you use it? You could use it for some common places where you already use. For example, when you open your Netflix or your YouTube, it will give you some recommendations for the movies, right? Or videos that you want to watch. It wants you to sync into the system. Again, that's a predictive model which you're using. In medical diagnostics, again, farming up risk score, any of these risk scores, these are all predictive models. Financial forecasting, where's Nifty going to go after what Trump tweeted, right? You want to know that. You have the AI assistants, and of course, you have real world predicting astronomical movements, predicting earthquakes. You have all these things where prediction is really there. And AI literally changes that. So machine learning has been around for a while, but I think it's in your hands, right? It used to be very difficult, complex. Now it's something which, a first year medical student can actually make a model of his own. So machine learning, you have supervised learning and unsupervised learning and reinforcement learning. Supervised learning is basically where you have input with labels. So for example, you take thyroid nodules, right? So you have thyroid nodules. So you put labels on it. You have the thyroid score and you have the ACR score and so on, right? So you have label data over there. And unsupervised learning is when you have the data, you allow the AI also to generate the labels on its own, right? So you have data without labels. So you're just giving unstructured data and then it can then generate some labels on its own. And then you have reinforcement learning. For example, some examples would be some of these chess algorithms like deep mind and so on, right? So which kind of learns by trial and error and so on. And then that's the field which again, Tesla probably is also, the automated system there works. So let me give you some examples of all of that. And for example, supervised learning, one clear model could be blood glucose predictions, where you already have a data set which you have, and you saw that whether this particular, let's say a food item increases the blood glucose or not, something like glycemic index of the same. I think the one which we had developed model earlier is a thyroid nodule classification. For example, you have the data set and you label it, and then you develop a supervised learning system over there. So that's supervised learning. And then you unsupervised learning, where you feed in the data without any labels. For example, let's say you have a lot of CGM data from your patients, and the model then looks at the CGM glucose patterns, highs and lows, and then clusters patients with similar profiles, right? No one tells the model what groups they are, right? So it kind of groups them on their own looking at the data pattern. So that's unsupervised learning, right? So if you take any machine learning workflow, you'll have to first collect data, and data is the key part of it. Then you process the data. We'll see all these steps. So after Shahir completes his thing, we'll actually use ChatGPT. A lot of you have access to that. Last time we had done a quick survey where a lot of you said that you're paying for ChatGPT. So if you have a paid subscription of ChatGPT, this is something which will be very useful. So we'll show you an example of that as well. So we'll do a data pre-processing. You train the model, then you'll evaluate the model, and then you'll use it for prediction and deployment, right? So for future prediction. So that's how. So we'll do that process step by step. We've already done it once. So I'll show you how we have done it, and so that we save time there. So that's how we will do. So this is just an introduction to machine learning. Now, Dr. Shahir is going to give you a classical example of a computer vision type supervised machine learning model, which is Google Teachable Machine. Google Teachable Machine, the reason why we have chosen that, like I said, is very much in tune with medical images. It's going to be very useful for you. So have a look at this, right? And then we'll come back with more ideas to share. Dr. Shahir, we hand it to you, and please take the stage.
Thanks a lot, Dr. Lakhani. I haven't heard of a more better introduction till date. I've been through any places. Well, the idea I can see that you have about the use of AI, particularly because I think it's medical science is just a very small part of it. Financial world is probably where most of the AI is being developed and deployed. But the next big thing, obviously, is the medical science, which is where it is coming. And I liked your examples of how companies that have leveraged AI are going ahead in the race, literally. Like you took Tesla's name, right? Their whole thing is based on the FSD being rolled out in other companies using their AI algorithms to drive their cars. So it's always the case with humans too, doctors too, companies and associations that actually use AI. They are at least they get a 10x leverage, I would say, in terms of where they will reach. And I thoroughly liked, and you made my job a lot more easier by that concise and great introduction. Thanks a lot, Dr. Lakhani.
Thank you. Thank you, Dr. Shahi.
Great. I'll start my screen share and let me take you. All right. So today's agenda is definitely going over the Google's Teachable Machine, an example really. But I want you to lead into that, right? When you look at it, then you should be able to understand everything. So just bear with me while I just take you through the motions a little bit on how we reach the point where Google's Teachable Machine comes into the picture. And I cannot emphasize more on the fact that Google's Teachable Machine is it remains the most simplest tool. It's not that something it has been created now. Like lots of AI has blown in the recent past. Like you've been hearing more of AI in the last 1 or 2 years, but Google's Teachable Machine has been doing this for last 5 years or so. And I can actually relate to what Dr. Lakhani is saying about Teachable Machine, because when I was doing my DM and I was doing all the I was basically it was mainly for writing papers, because writing AI papers were like more readily accepted. That was my selfish motive to try out AI. But then one of my professors challenged me saying that just doing it on data sets and all is fine, but can you classify X-rays based on AI? Like that's the thing you should be doing. Then at that point, going through code to do that was extremely difficult because there was no LLMs to suggest code or anything. Even now, it is a little bit difficult, but it was way difficult back then. So somehow, surprisingly or serendipitously, I came across this teachable machine tool, and then I tried it. Then I did it again and again and again. Went back and read everything about teachable machine that existed on the internet, and then I got this understanding of teachable machine, which allowed me to eventually write the code for a image classification model that got published in the European Respiratory Journal at that point when I was doing my residency. And that got me into the industry where I am. So a lot of that is actually creditable to teachable machines. So I totally second what Dr. Lakhani told about teachable machine. This is something anyone aspiring to learn machine learning, particularly image classification, must do, because this is the simplest way to learn it. So I'll just get started with how the images are classified, right? So if you think of machine learning, which was just introduced just now, right? So when you come to image classification, right? So you could easily relate to it, right? So more like you have to think of it like, how do humans learn? That's exactly how the machines are going to learn. So that's the genius of AI. That is, it has tried to replicate what humans were doing. So if you imagine, right, the child is asked to view an object, the child will actually, if you remember your own childhood, you might remember, right? Like you would very intently look at the colors. You might look at the patterns that are on the colors. You might look at the edges. A lot of things you will not do as an adult because you just take it for granted. But when you are actually learning it, you were keenly observing the texture, everything about the object that was in front of you. So feature detection is something that AI also does. So when we provide images to an AI, say a thyroid nodule or an ulcer or diabetic retinopathy, right? It tries to find out what are the features that are very typical of it. Does it have pointed corners? Does it have a good surface? Is it like cotton wool spots? Whatever it is. it tries to extract those features. So AI will also do that. And then so many times, like if you remember with your learning of language, so a lot of it was not exactly taught to us, like and means and. There's no way of actually telling you something that you'd never know, right? For a child is learning the words. So a lot of it, the child actually imputes. It understands by looking at the context. So whenever it's learning a new word, nobody goes and not many times they go and explain the entire meaning of context of that thing. But after hearing from like 10, 15 adults, the child actually starts understanding what is the meaning of and what is the meaning of or whatever other words it is learning. So AI also has that capacity to learn from the context, will come how it will be used. And the third thing, which is very important for machines to learn, is the supervision. So you saw the unsupervised, supervised, and reinforced learning slide with Dr. Lakhani. The image classification that we do in Google's Teachable Machine largely revolves around doing the supervised learning. So I'll tell you what it is. Right? So if you look at this image, it is just like our school days where we were learning under supervision. So if the teacher says, please draw a tree, we will all draw a tree, right? Or the teacher asks us to draw a mountain with the valley and the river, right? So we all do the same, right? So machines also need some supervision. So you have to tell the machine, look, your job is to distinguish in a given photo or a picture whether it's a ulcerated diabetes foot or it's a normal one. Is this a multinodular goiter or a nodular goiter or a diffuse goiter? Whatever the challenge that you want, so you have to explicitly tell it, right? And what do I mean by tell it? There is no way of telling AI. So what you do is you actually generate data sets. So if your job is to detect diabetic retinopathy versus non-diabetic retinopathy, you need to collect images of diabetic retinopathy in a folder, and you should collect images of normal retinal images in another folder, right? And then expose AI to each folder and name it. And even then, right? Even then, for the AI, please understand this, right? For the AI, so many times it does not matter what the real truth is. What matters to it more is what have you trained it on. For example, by mistake, I put all diabetic retinopathy images in the normal retinal images folder and vice versa, right? So I have basically flipped the script. And now my things are all reversed. The learning is reversed. When I train such a model and when I challenge it with a normal retinal image, it will call it out as diabetic retinopathy because at the time of learning, we have given it that as the ground truth label. We have told it that in this folder, there are diabetic retinopathy images. And whatever you learn from this, you are going to call it as diabetic retinopathy. But by mistake, I put normal retinal images and swap the thing in the other folder. Then it is just going to learn that. So you have to understand that garbage in and garbage out, right? Or if you teach the reverse thing, it will just learn the reverse. So your AI model is going to be as good as your data set. So we will see in practical examples how that plays out. This is a very simple schema of how the image classifications and all matter. So this is a very superficial thing. So what you are seeing here is that there are lots of images. Say you want to separate between cats and dogs. That's a very favorite starting point for ML folks. If you're doing this, then the model basically gets trained to identify a dog and a cat. And then given a new picture, it will say whether this is a cat or a dog. And the way it could do is there are certain things that are very characteristic in cats. For example, the nose is a different style, the ears are a different style, and so on. And the same thing holds for the dogs. So those common themes are identified by AI model. And whenever a new picture is given to the AI model, which it has never seen, then it is going to compare it against the feature map that it has and going to fit it. Does the ears look like those of dog or a cat? Does the eyes look like those of a cat or a dog? Or the skin texture or whatnot? We don't know so many times because it's a huge feature space. Sometimes it's very difficult to know what it is truly understanding. Maybe it's giving all weightage to the whiskers. We never know. And sometimes we know there is a way to know it, but sometimes there is no way. But in any case, a model learns that stuff and it is able to classify. And we are going to do it on medical examples. So this is a picture. Why I'm showing you this picture is because we already to think of it like our brains are also similar to machine learning models. In fact, this called neural networks, right? Neural net that comes in AI. That is actually copied from the human neurons. So what happens is like they have tried to copy how our brain works. So in a way, I can reverse engineer it and say that our brains work like machine learning models. And there are so many patterns that we are going to actually discuss and do in Google Teachable Machine that are already in our brains. So if you look at these two images, these are obviously very contrasting images that I have provided here. And if I were to ask you, which of these two persons would be more prone to developing, say, tendon ruptures, or maybe like Achilles tendon rupture or something? So our brains will naturally go towards the muscular person because we know that people who work out a lot, or maybe there are gym related injuries, or people who are in running and all that, they might have injuries related to tendons. So you're more likely to label this guy, right? You're going to call out this guy as more likely to develop tendon injuries than this person, right? But if I were to flip the question and say, who is more likely to be having obstructive sleep apnea, then obviously you will point out to this person because that's how our brains have learned patterns, right? So, given a patient's profile, our brains already do the neural network, the machine learning thing, and place this person in OSA category and this person in non-OSA category, this person in tendon rupture category, this person in no tendon rupture category. And if I were to ask which of these two are more likely to have type 2 DM, then you're most probably going to put this person in type 2 diabetic status versus this patient. And same goes for resting bradycardia, right? So this patient seems to be athletic. So our brain is already doing the same kind of things and placing this. So AI is also, the models that you're going to train are also going to do the same thing. Whenever it is challenged with an image, it is going to put it in one of the two categories, right? Or three categories, whichever the way we have trained, right? So this is another example. You probably see the striae, the central obesity, the moon phase, right? So I know this is all endocrinologists, so you will be very quick to spot the Cushingoid features. So this is again an example of patterns, right? So if I were to train an AI model to identify children with Cushingoid features versus none, then I am going to show pictures of these kids and then the normal kids. And AI model is going to learn, if I show it 100 kids with these features, and then I show 100 normal kids to it, the same way like we learn, right? So we understand the obesity, the striae, and this moon phase and these kind of features. Same way, the AI is also going to learn these things, and you just have to show it enough pictures. That's all. So it could be when the difference between two things is very big, say for between this kid and malnourished kid, for instance, the difference will be so big that if you maybe show 10 pictures of these kind of kids versus 10 pictures of those kind of kids, right? The model, it is enough to learn the difference between those. But if I were to show these pictures of Cushingoid features versus another 100 pictures of obese kids, right? Like morbidly obese kids, right? Even though they don't have that problem, the AI's ability to learn will be very difficult. Just because it is difficult for us also, right? Because it will be because the features have reduced now. The differences between the two things have reduced. So the AI model will find it very difficult to learn and it may not learn very well, right? And we'll tell you how to check whether it has learned very well or not. This is another example of a pattern. Okay. So if you look at the pattern, you are able to this pattern, the Addison's pattern, and you can easily spot this. But if I am going to create a model to distinguish between Addisons versus no Addisons, then I need to give, say, 100 or 50 or 40 or 80, depending on how much different are the two groups, that many pictures of cases of these kind of pictures and controls that look like this. And if I show 100 hands and 100 hands of normal people like this, give it to human or give it to a machine, both are going to learn some features, right? So humans might learn the hyperpigmentation and so on, and the lack of those in controls. And then whenever you are challenged with either of those two hands, you're going to identify and classically put them. So machine learning is also going to do the same thing and going to put them in one or the other categories. No, so that's exactly how we are going to be doing our examples, right? There are many things that you can do in ML, but largely we'll be revolving around classification algorithms today. I'll call it classification because you are separating them into 2 or 3 or 4 or 5 categories, right? Like type 1 versus type 2 diabetes mellitus is a category classification. Whereas if you are predicting what is the HbA1c of a given person or a TSS level, then that becomes a regression. So in Google's Teachable Machine, what they have enabled very easily to do is a classification algorithms where you can feed 2 or 3 categories of images, and then the resultant model will, whenever challenged with a new photograph, will put them into one or the other categories. And if you are going to be writing some paper using this, which obviously you should and you must, given that you have lots of data, and you should try that. And this whole purpose of that is today's thing is towards that. So you will need to tell something about the sensitivity and specificity. And if you just brush up your little bit of stats that we learned in our third year MBBS, so this should be very easily doable. And before we delve into the actual this thing, I just want you to know how exactly Google's Teachable Machine is able to do these classifications. They are able to do this because now you see this picture, right? This is the famous picture of the president of US, not the current one, but the renowned one. So if you look at this picture, always these pictures are made of pixels, right? And pixels have some value. It is basically a number. If you understand it right, image is nothing but a number projected on a screen, adapted to a color. The number decides what is the strength of the color. That determines how the picture is going to look like. And then what AI does is takes a picture and extracts the pixels from those pictures. And then once you have a pixel extracted, it will lay out all these things as one line, single line. So for AI, it does not matter what the picture or looks like. Who is this president of US or a common person from the US or India? It does not matter to it. All it does is it takes those pixels, flattens it out, treats it as a vector, as a value, and then uses AI like how we used to use the machine learning, the logistic regression or the linear regression, similar things it does, and gets an out. Then given a new picture, it is going to flatten that picture out and going to compare against the classes. So if your classes are type 1 diabetes versus type 2 diabetes, it's going to compare against those and says, okay, this vector, this number belongs to this class. It's not so much concerned with the images. It's just the numbers that matter at the end for AI. We might interpret it in this fashion. And to understand fully what we are going to do next after this slide is that any data that is given in AI is divided into training, validation, and test set. So what happens is, think of it like your examinations. So in our first year examination, imagine that this is training, like all the first year we went through NAT, biochem and physio classes. The validation are like your internal examinations, like internals. So what happens is, model learns on these training data, and then it does on the validation thing, it learns whether I can pass the exam or fail. And it tests itself and knows that, okay, after first internals, I realized that I was not good in anatomy. And I knew that I had to improve that a lot. And I did all that. And eventually I wrote the final exam. And depending on how good your learning is, how good your data is, that's how you're going to perform in this test. And in terms of image classification, Google's Teachable Machine thing, the test set would be composed of two classes for simplicity. Say class type 1 diabetes and class 2 test class 2 diabetes, type 2 diabetes. Then how good the model has placed. So in the test set, the labels are never shown. So what happens is, in training, your images and the ground truth. By ground truth, if I'm showing an image of multinodular goiter and diffuse goiter, then it is going to know that this is multinodular goiter, this is diffuse goiter. It learns and learns and goes over n number of times over it, like revision. And then once it has learned it, the test comes. In the test, you are not supposed to, the model does not see the labels. It does not know whether this is multinodular goiter or diffuse goiter. It just predicts it is multinodular, this is diffuse, this is multi, this is diffuse, this is multi, and so on. And eventually, we have the ground truth. We know which figure is what, and we are going to test it and say that the sensitivity of this model in detecting multinodular goiter is this much. The sensitivity of this model in detecting this is this much. The accuracy is this much. The specificity is this much, and so on. Okay, so we are going to see an example now of Google's Teachable Machine, basically consisting of, I have taken a very simple example, which basically the simple example means that the differences between the two groups is so big that it is like a slam dunk. There is nothing big deal about this. Like, even a kid, if you teach what is a healthy skin and what is an ulcer, is going to do it correctly. The thing is, these are diabetic foot ulcers, and these are normal feet of diabetic patients. Like, I've just used it so that we can appreciate what are the nuances that go through this. Then I have a thyroid scintigraphy images, it's a little vague, and we are going to do that also, and we're going to see what challenges we face in each. So now I'll dive into the teachable machine itself. Okay. So I hope you can still see my screen. If not, please let me know. So we are going to do the machine. If you just type this, you will get this link on top, right? Teachable machine. Like, you should bookmark this or something. And you click on this, right? You get this screen. And if you see here, there's a very big thing saying get started. And there are multiple things you can do. You can create a pose, AI, the audio and image. I think image is something that is very relevant to medical community, because a lot of our diagnoses are based on the physical characteristics of patients. You can, of course, do an auscultatory project with the audio thing, but for the current thing, we are going to do an image which is very simple. And believe me, there are still not enough papers that are published using this thing. So there is a lot of scope. Don't think that something is too simple. You can always create an AI algorithm out of it and write the results, send it as a publication or something. You never know what that paper is going to land you with. So don't think of anything is too lowly to do with this thing, because not many people are doing this. Not many people are actually ahead in this race. And thanks to the Endocrine Society of India and SAIL collaboration, I can see that the people hearing these talks are going to be benefiting definitely from this. So after this, you should definitely go and try your local images and start writing publications out of that. So I'll just click on this image. Once I click, there is an standard image model or embedded image model, it is always good to select the standard image model, and you land on this page, right? It's a very intuitive thing, nothing big deal about it. So here you see there are two classes, right? Class 1, class 2. You can add more classes also, but for simplicity, I'll keep it binary classification, right? So the first class, I will add it as ulcers, right? I'll just name it as ulcers. I'm going to add all images of ulcers here. And for this one, I'm going to name it as healthy, right? Healthy skin. Yeah, just can name it whatever you like, but you should just not flip. I mean, if I've written ulcers here, I should upload ulcer things. There's an upload button here. So I go here, and as I told you that I'll be taking the ulcers versus no ulcers data set. So there is one such data set. I'll provide you the links for these where you can download this and play around with this. Or if you have your own things, you can do it even there. So you see here, there are two folders here. So this is ulcer folder. So I'm going to just select some images from here. Okay. All right. Then I take healthy skin. I go here. You just choose images. This is like basic, simple, whatever you do in your regular stuff, right? This is not more complicated than that. I just go back to my data set. There is a healthy thing, right? So I just copy all of these, right? It is here. And now you see, always make sure that you have uploaded in the right folders, because by mistake, if I put healthy skin in ulcers and healthy skin, it's going to learn ulcer as healthy and healthy as ulcers. That's something you should be careful about. And then imagine just two steps I did, just uploading the images, right? Then you see here, train, right? That's all. You just click on it. An AI model, believe it or not, it's a deep neural network that is being trained as we speak. You should give it a few moments for it to train, and you can see how it is progressing here. And we'll go into what these numbers mean a little later, but we'll learn the more important stuff. It is about to complete. It is learning what is common between all the ulcers, what is common between all the healthy skin. Okay. So see here, the model has been turned. Now I will, here there was an option here of webcam, right? So if you created a webcam project, then this webcam things are what will be needed. But here we created out of files. So I'll start with the files. And now let us see. Okay, so now I'll pick up a picture from internet. Right. Let me just get a ulcer diabetic foot. Right, there are so many things, right? So let us take this, for example. I'm doing all these easier things because obviously it's for learning, right? So I'm going to save this image, name whatever it is, naming me. Now it has been saved. Now I upload it. I go to this thing. I take this. See, it is calling it ulcer with 100% confidence. Okay. Now let us give it another example, right? Maybe something which is less obvious. Let us see this. Okay. To save it. Saved. Now I'll go here and upload this image. Okay, so we need it in JPEG or PNG format. So that doesn't work. This is apparently not in that format. So let us use a little tougher thing. Okay. Maybe this one. It has like less amount of ulcer. So now I come here. I upload this. Now you see the confidence reduced, right? From 100%, now it is 98%, but it is still correctly calling it as ulcer. But if you see the other 2%, right, is towards healthy. So basically, whenever it is over 50%, then you're going to call it as ulcer or this is over 50%. Now let's take a even tougher thing, which is even lesser ulcer, maybe like very minimum, maybe this one, right? Let us see. Okay, I will use this. See, now it is calling it as healthy 99%, right? It is ignoring the small thing because it has all these images that we have here, right? They are all gross images. So they are all gross images because the model has never seen such a small ulcer. It is, it is think. And to be fair to the model, you can see that most of it is there. It is more resembling the ones that we provided as normal, right? So it is going to call this out as normal skin, right? And so model can make mistakes like this. Now it is up to us to what do we ground truth this as. If we are ground truthing this as ulcer, which I think it's rightly should be, then this is a false negative that the model got it wrong, which means the sensitivity false for the model. But if we call it a normal thing and you say that it's not so much of an ulcer, then it has definitely got it correct and the specificity for the model was high. So it depends like that. So this is a classic way to understand that it fails near the edge cases, right? And if you want to do well in the edge cases, then you need to provide the edge cases, right? If I give it 100 more images with very small ulcers like this, then it is going to learn that, okay, this is also an ulcer. Even though it is small, it is still an ulcer and it will correctly put it in the ulcer category as opposed to the healthy skin, right? So, more the merrier in AI and cleaner the better, which means that more data you give, the model is that much better. But the cleaner the data is, that much better the model will be. Right? If you give very unclean, right, like you give all these edge cases in both sides, for instance, you ask maybe a non-medico to annotate these images and put them into ulcer and healthy skin. Possibly somebody is not experienced with these things, they can do mistakes. Then what happens is your model will also struggle to learn what is common, right? Because what will be common between healthy and an ulcer skin, right? It's very difficult for the model also to learn. So to make life easier for everybody, we should do a very clean annotation whenever we are training data, and we should have more data as much as we can, not necessarily always, but sometimes you should aspire for more data. And if you really want to, for your use case is all small answers, right? Then your training data should have small ulcers. If you train it all on big ulcers and you give small ulcer and then ask the model to do it, it's not going to do. So, if your use case is, you should tailor your thing to that. Now, what you can do, say you have trained a model like this. Now you want to publish. What are you going to do? So, what you're going to do is you are going to have, say, 25 images of ulcers in one folder, which has not been used in training. So, always you remember, right, the slide, the training and test datasets are always separate. So, whatever it is trained on, you can't use the same thing for testing because then the model would have already seen this in training. So, it will obviously do it right. And that is not counted. So, whenever
Can
you are, yeah.
can I interject one? There's a
Yes.
question from Dr. Lakshmi, which is exactly that. Can you just explain to us again what exactly is a training set and what is exactly is a set used for making a model?
Great question. very
So
high
validation and testing set, how does it differ? Can you just reiterate that fact again?
Yep. Great question. Always AI, the thing that is sacrosanct is the separation, right? Like the church and the state, we have a separation of training, validation, and test. So you never mix them, right? So what happens is when you're training a deep neural network thing, say ulcers and healthy skin. Now you've seen the example, right? So what it does is it gives it in batches. So consider this as AI model, right? Suppose there is a AI model somewhere here. So what the AI model is going to do is like at a time, 4 or 5 or 6 or 10 images are provided to the training. And during training, it is going to say that this is the ulcer picture. This is a normal healthy skin picture. This is ulcer picture. This is healthy. This is healthy. This is ulcer. This is ulcer. Healthy. And so on, right? And then after one round is done like that, it will go here to validation, right? Here it checks how well it is doing, how well it is performing here. Then it will also have access to the ground truths here. After performing here, it will be told, okay, this was ulcer, this was healthy skin, this was ulcer, this was healthy skin. Then if the model got it wrong, say in validation it got the ulcer as healthy, then it is going to tell the training part to adjust the weights, which means the model starts learning that I did this wrong. I need to do it correct. So I need to do something which is something I learned wrongly. It will go and correct itself and comes back again. And another round of training happens, another round of validation happens. Again, it will make some mistakes or it does it correctly. Even if it does correctly, it will learn that I did it correctly because of these things. If it did wrongly, it will learn because of these things and goes on and on. And after we finish multiple revisions, think of it like revisions before the exam, right? So after 50 or 100 revisions, right, it is going to sit in the exam. In the exam, the ground truths, which are the marks, are never shown, right? Like what is the true answer is never shown. Only the questions are given. It performs on this test set and it will never know the labels of these test sets. So it will never know what is ulcer or what is not. It's a human thing that actually compares it. Okay, you called it ulcer. I know it is not a ulcer, so you got it wrong. You called it healthy. I know it is healthy. You got it right. You called it ulcer. I also called it ulcer, so you are correct. So it only assessed here and it is done. It is finished. The model training is finished. You get to apply the model on a test set only once. Whereas in here, training and validation, you can go n number of times depending on how much compute you have or how much time you have. You can go as much number of times and keep on checking how well it. In the final one, you're going to test it on the test set. So I hope you have any more questions on this. I'd be happy to.
No, that was the question. So I think great. Go ahead. Sorry.
Okay. Yeah. So now, as I was saying, like now you want to publish this, right? So suppose you have in your clinic, you are seeing acanthosis nigricans a lot in your maybe metabolic syndrome patients or something like that, or in your NASH patients, for instance, and you want to write a paper that AI can scan the skin and identify acanthosis like that, right? That's your hypothesis. Okay. And you have sufficient patients coming in, you can take their picture with their consent and only the picture of the skin and where this is there. And then you take it from the patients that they don't have acanthosis. And you collect another picture like this, like healthy versus acanthosis, for instance. Say you got 100 images of cases, 100 images of controls, right? You got this now, you train the model. Now, how are you going to publish this, right? So the test set is missing here, right? The test set is missing. So what you have to do is you have to keep 25 pictures of acanthosis separately, 25 pictures of normal skin separately, right? And then one by one, you have to upload it here, right? Like how I was doing and record the outputs and say out of 25 acanthosis patients, acanthosis skin pictures, it got 20 correct, for instance. Then it is 20 by 25. That is the accuracy of your thing. You can also call it sensitivity, but I wouldn't burden you much with the definitions. Once you have those numbers, it's a very simple task. Maybe you can put it to ChatGPT, it will tell you all the statistics there. So the important point is it got 20 out of 25 right. And in the normal skin, maybe it got 15 out of 25 correct, which means that 10 out of the 25 it called out as acanthosis patients actually wrongly. So it did a mistake there. So you have to account for all that. And then you say that the accuracy of my model in detecting normal skin is 15 by 25 into 100. And the accuracy of my model in detecting acanthosis patients are 20 out of 20 by 25 into 100. And then you're going to report your results in your thing and say that I have built an AI model using Google's Teachable Machine. You can go and into their papers that they have in their blogs, and you can cite those papers and say, I use this deep neural network that is available, hosted open source, and I ran these things. I labeled my data like this. I had this test set. I applied. This was my accuracy. That's it. And then in the discussion part, you can always discuss that acanthosis is important for this, that, and AI is not being used in this thing blah blah blah, whatever it is, right? So don't think of any problem as low, right? Go for it, do it, right? And you never know, some company might pick it up and say, okay, let us build this model at scale, at production level. So they are going to source thousands of pictures and they are going to do all production level hyperparameter tunings and so on. But for your paper purpose, like what Dr. Lakhani was like harping on this Google Teachable Machine, this should be something that you should seriously pursue, right? But while you are doing that, so if you are going to publish this, then you need to actually look at the advanced things here, right? The advanced things. So you have to click on this advanced things. You will see these are the epochs, the revisions that I was talking about. So once you try it on your own, don't get worried about, what this, I don't understand epochs, bad size learning rate, blah, blah, blah. None of this really matter. That's why they have hidden it, really. Yeah. But, when you are doing it for the paper, it might matter. And once you do this multiple times and read about this, once you have an understanding of AI works, right, these are all very simple things. So this is basically 50 times it did a revision, and batch size of 16 basically means that at one time, 16 images were being given to the model to learn. And learning rate is something which is very interesting that you should probably read up on. That is like a little bit of math, but it's very interesting how you discover the truth, how fast you want to discover the truth. If the learning rate is very big, then you can hop over the truth. But if the learning rate is very small, then you might move so little each time that you can get stuck in a very small corner and think that is the end of the world, right? Like how 500 years back people used to think the earth was flat and you will fall off the planet if you reach the end of the earth, right? So that will be, if it is very small, then you risk being in that rock swell. But if it is too big, you risk hopping over the truth, never discovering it, and might have to make do with something that you find. So ideal thing is what is really required, but this is only for learning. Don't bother about these things. There is something called under the hood. After you go in advanced, right? I'll just show you again. Once you go in advanced, you'll get under the hood. Okay. So here you see whatever I train my model on, right? Here you will get some graphs. Okay. And some confusion matrix. A confusion matrix is nothing but your, see here, it is in the test set, right? Inside it, it will have a 15% test set always. So it is telling you there. It is not telling you, this is the validation set. It is not telling about the true test set that you are going to provide one by one, right? So there, if you see the accuracy of healthy skin is 99%, accuracy of ulcer is 100%. Obviously 100% because it is so obvious that even a first standard kid will probably learn this. So it has gotten it very nice. And you see the confusion matrix. But you should not report these numbers. You should report these numbers. But your true test of your model comes from your test set, right? Which you have kept it separately and you're going to upload it one by one and note down the responses. So here, if you see how, it called out one healthy skin patient as an ulcer. I don't know. We have to go and see which patient this was. And if you actually go and see this patient, it could be very well possible that this patient was dicey. Matlab, there was a very good chance that this patient actually had an ulcer or there was some feature that looked like an ulcer. It is very much possible. If it's a very good model, then even if it causes an error, and in fact, I have observed it in my in my line of work. Okay. So we were creating this cardiac age model. We were detecting the age of a patient using their ECG, right? So the training was of ECG and that the prediction was age. Then I was getting this delta, which is basically a difference between the two ages, right? Then I found one patient had, or a few patients had delta of over 100 years, which means their actual age and the difference of the cardiac age was over 100. And I was like, what is happening? Then I actually went into their record and I actually found they were, so instead of 36 years, it was by mistake, it was written 136. Right? But the AI model was correctly calling it as somewhere around 34 or 33. And that is why the delta, though, was big, but that was coming from how we wrongly annotated the test set. So sometimes AI is actually more correct than even humans, right? That is very much possible. But for our purpose, let us believe whatever data set we provided is the ground truth. And whatever the model does is their predictions. And we are going to evaluate the model. We are not going to evaluate the human annotation. Okay? So you will have this accuracy per epoch thing. And you don't need to worry yourself too much. You can put this picture in chat GPT. It is going to tell you everything about what to write about this. But I'll tell you what it is basically telling you is how, after how many cycles it is learning, right? If you look at it here, mostly it is learning after the first cycle itself, almost. It is so easy. The problem is so easy that it learns so well. Otherwise, it will take a little bit longer to learn like this. And then this graph becomes important. And here you see the graph is actually very important. So what is happening is here you are seeing this test loss and loss, right? This loss is coming from training. So the loss means basically the difference between the ground truth and your prediction. So think of it like if the loss is very less, then you are doing it correct. And if the loss is big, you're doing it wrongly. So what it is showing is while the model is learning, it is learning better and better and better with each subsequent model because the loss is reducing always for the blue line. But if you see for the yellow line, which is a test loss, which is not truly a test loss, it is a validation loss here. So here it is keep on increasing, which means that you don't need these many epochs. You can actually stop at 10 or 5 or 6 or 7 or something. This is the thing that you might need. And you can definitely start just create classes. Like I'll show you one model with 3 classes. Okay, now if you want to like export the model and keep it for future use, you have this export model thing. You just go here and upload my model. You will get a shareable link.
Yeah.
You
So
get
while that's being done, I think for again the endocrine community, I think for example, Thyroid's score. So you can have multiple. Here we have two. You could have multiple class. So you have Thyroid's 1, Thyroid's 2, Thyroid's 3, Thyroid's 4, right? So you have images of all of them. Try to look for images. I think there are ready-made data sets also available. So just put them and then put a decent number there, and then you'll be able to just upload the thyroid nodule image, and you will get the predicted Thyroid score. So I think that's one way of having multiple classes. For example, again, retinopathy, proliferative retinopathy, non-proliferative retinopathy, mild, moderate, severe, you could sub-classify them and upload the data accordingly.
Yep, that's a excellent example of a multi-class thing. So here, what I did was just exported it as a shareable link, right? This link you get after you click upload my model, and I just paste it anywhere in my browser, right? It is going to load this model, and you can always, so you need not train the model always, right? So once you train it, just keep it. You can download a copy of it for reference. So you have that option also available, just in case the reviewers are going to ask you for that. We generally don't, but it's a good habit to have it. You can always use this to upload images from whichever browser is there. Now, just a simple example, it won't take too much time now that we are very well grounded. I'll just show you one example of a multi-class that Dr. Lakhani was saying. But I have a class of just this goiters, actually. That's a data set I have. And I can provide you those data sets. So I'll just call it multi-modular goiter diffuse and modular. Let's call it these three. And I am going to again just upload, just we did. So I have these thyroid scan images. I'll provide you the links where I got this. So my first thing is multinodular, right? So I'm just going to pick it up, right? Now you see there, these are scintigraphy images of thyroid. So here you have to choose the same kind of orientation, right? So you can't choose RAO and then challenge it with an anterior image. So you should, if you're giving anterior, you're always giving all anterior. And whenever you're testing it, that time also you're testing it all with anterior only. So that's something we should always do. This is nodular or no, this is diffuse. We should be very careful. Here also I'll take the same projection. So if I need to train it, right? So I have to give uniform kind of data always. That's what I'm doing. And here is the 3 thing.
So these are scintigraphy images, right?
Yeah, these are
Okay.
scintigraphy images. So for the purposes of endocrine thing, I went after something endocrine, but they didn't make much sense to me, but I hope it does make to you. Okay. So we see we have 104 images, 74 images, and 14 images. So now you see the challenge here is that with 14 images, for it to learn is very difficult. Right? Whereas for 104 and 74, it will learn well. So we should probably give similar amount of images, but just for example, I'm just taking this. You can do multiple iterations. It is training here, right? Now the model is trained. Now I put it to file and let us find some images from the internet. Let's use called scintigraphy. Anterior I'll put so that I can find some images. I don't know which one is a very characteristic one, but let's take this because it's similar to how we have this 3 centimeter all is not there. So usually you should give as close to the training data as possible, but for logistical purposes, we'll try this and we'll see what happens. If it is a very obvious thing to learn, then this would get it correct. Let us calls. Oh, it's calling it diffuse. I don't know what's the ground truth. Yes, sir.
Yeah, it's a, yeah.
Okay. So it could go both ways, right? This could be some edge case.
There's one from Radiopedia which is better. The one we had. This one. Yeah.
This one?
Yeah.
Okay.
Might be. Again, we don't know what kind of data set we had, but
Yeah, exactly. But let's try. Okay. So this is how we learn, right? So we have to do things and keep seeing. Again, it calls it diffuse. So there is something.
Yeah, in the data set.
So it's like that, the data set we provide. So these are the challenges also you're going to face. So it's the better annotated and confident data we have, that's how well this is going to be. And one should probably start with binary classification always instead of going with bigger ones like starter. Once you learn this stuff, then I think sky is the limit in terms of what you can do very quickly with this incredible tool. And to tell you honestly, this has been there for much longer than the AI boom that we are seeing. So it has taught a big generation of people. It has taught AI, and I am one of them. So I am actually very happy to put this. And still, I would say to the audience that don't think it is too late. Don't think that you are getting it now when AI has been going on for 5-6 years and there's a lot of boom and all that, right? I'm telling you honestly, I'm in the industry. We have not even scratched the millimeter of the skin. So it is so much. Each and every aspect of medical practice is going to be affected by AI. And even if 10,000 or 50,000 doctors are going to start doing AI today, it is still not going to be enough. We will still have scope for doing things, improving things, and this thing is there and it should be led by doctors and they are best placed, right? Like I am like an engineer here, literally, because I don't know the ground truths as good as Dr. Lakhani. So imagine what would be the thing with true engineers, right? So they are never going to be able to do this unless they are guided by you. And image is something that is so easy to learn. You should go for it, try it, and tinker with it. And I would say if you want to note down the where I got the data sets and all, and if you want to like sometime reach out with queries or anything, but these are the data sets you can find at these sites, the one that I did. And we had taken more than enough of my time towards this. Dr. Lakhani.
Absolutely. It's fascinating. More the merrier, you said. Like you said, I think that's what it is. Beautiful. Thank you, Shahir. That was wonderful. We'd planned something, but I think we'll leave it to next time because anyways, what I realize it fits better in the next lecture. So we'll do that. So we'll basically right now take this remaining time to take questions from the audience because there are some interesting questions which are there. And Shahir would like to have your answers for that. So let's start with that. Let's start with my question, which I have before to privilege and take before others. What I'll ask is, we have heard of this term overfitting, right? What exactly is overfitting? This is something we keep hearing when you say that is your model overfitting. What exactly is that?
Brilliant. Actually, that's a very good thing. In fact, we have that right in our last training. I'll actually share my screen, go back there. But before that, I'll just share the conceptual thinking of this. This is very easy to understand if you think of it, how you prepare for an exam, right? So say a first year MBBS kid, I give that kid, instead of training that kid on actual subjects, right? Anatomy, physiology, and biochem, I give this kid 500 questions spanning all the three subjects, right? And tell that kid, right? You just study this. You're going to, you ratta maar lo aap, ratta maar lo, itna maar lo ke nothing. So then what happens is like that ratta is basically the number of revisions. So if I do 500 times instead of 50 times, then what happens is, so it starts like this. First time I read the thing, I will probably score 40% in exam. Oh, that's overestimation, say 20%. Next time, like 2 times, I maybe 42, 3 times, 45, 5 times, 50, 6, 10 times, I might get 70%. But after some time, right, if I do 100 times revision, for instance, then my worldview narrows and I only look at that question and I look at that answer. I lose the ability to generalize.
Correct.
Then what happens is it just ratta maros that same images. It by hearts that this is ulcer, this is skin, this is ulcer, this is skin by hearts. Then what happens when it comes out of that exam into real world? Right? Say USMLE is given or the NEET exam is given. There they will test the concepts, right? Not going to test whether you did well by hearting all the questions. Then it fails.
Correct.
So the way that happens in ML model is when you allow the epochs to run too many times, just because you have the compute, you do it 500 times. After some time, it starts learning that by heart thing because it's just a machine. So what you do really is you ask it to stop after some time. When the loss that we were seeing there, the loss does not improve, or in the test set, the loss first it comes down, the loss comes down, then the loss starts going up back up in the test set. While your training keeps going down because you are just rectifying the whole thing.
Right.
So in your internal exams, you're doing very well, but you go to USMLE, you start doing bad after a point. And that's when the model becomes over. It only recognizes what it is trained on. It cannot generalize and it is bad.
Correct. Okay. Excellent example. So I think the idea really is that it basically you trained it so well that it does not see the concept behind it, the idea behind it. I think you need to leave it to a little bit of a sort of leaving it to the imagination, I would say. Sumit has raised his hand. So before we go to Sumit, there are a couple of questions we'll take from the chats. Pallavi has asked that do you need to annotate each of the image or is it okay to classify them, put it in respective folder? Shahir, basically, so again, just to tell Pallavi, you don't have to manually annotate. When Shahir was saying annotate, basically what he's saying is classify, right? So for example, you find a normal retina, you put it in normal retina folder. That's your annotation which you're doing. And if you find a diabetic retinopathy, put it in the folder of diabetic retinopathy, right? Correct me if I'm wrong.
Yeah, perfect.
Okay. Yeah. So that's Lavi. And I think somebody had raised their hands. If you could raise your hand again, we'll allow you to. Yes. Sumit, please go ahead.
Hello, sir. Good evening, sir. My question is, sir has told us to construct the diagrams break the diagrams into different parts and repeatedly teach the machine same thing again and again, similar kind of pictures to make the machine learn. It is, if we have proper data, but how are we going to feed that data into the machine through codes? It is only that we have machine but we have to write the code. how are you going to write the code? Are we going to use Python, or we are going to do some extra machine learning languages for that?
Sumit, what Dr. Shahir showed you was a no code tool, basically Google Teachable Machine. So you don't have to write any code in Python. You just have to take your images and upload it into the system. It's completely foolproof. You just have to go and put it up and it will generate the system. Now, to say what you're going to do with the entire thing is now made for you. The link is made for you. That link itself, if you open it, you will find a system where you have to just upload the image and it will give you the answer. So you really don't need to write any
Okay.
backend code for it. But if you want, you can integrate. Let's say I'm making an app. For example, I'll give you an example. Let's say I want to make an application for my field workers to detect whether the patient has diabetic foot ulcer or not. So I make the model, I train the model, I generate the link for it, and then I make a separate application, a front-end app, which uses that data, uses that model at a backend, and then uses. So for that, I need code. But for the routine use case, for example, what we're doing right now is research use case. For research use case, what you can do is you can share the model directly with your field worker or with your research assistant and so on, and directly do that. You don't need to write one single line in code. Everything can be done without coding, right? So that's why we chose.
So can we do
Google
this
Teachable-
with synthetic data?
Sorry?
Can we do this with synthetic data? Because in RNN and CNN, we have synthetic data.
No, we are not talking about synthetic data here. This is real world images that you're going to put, real applications, and not synthetic data. Will not be having AI generated images, or will not be having, you'll have real image sets which you'll be putting in for that purpose. We'll have, of course, different teachings for machine learning in the next session. But here we are right now focused on the image aspect of it.
Okay. Thank you.
Yes. Yeah. Few more questions will take.
Sir, one more question. One more
Yes.
question regarding this thing again.
Yes.
Sir, I am looking forward to make a machine based on neural diseases. So for that, I am planning to use synthetic data so that camera can predict disease beforehand, before a disease develops into a full-blown disease. So can I use synthetic data for that?
Okay. What
Can I
exactly are
use
you
this
trying?
machine?
No, what exactly are you trying to predict here? What kind of data are you going to feed in?
Actually, I'm working on a project on prevent sagging in army. Sagging means the seniors are being killed by the juniors. That is due to some depression or something like that. So depression is nothing but change in neural networks in our brain, and that has some different behavioral patterns. So if in some camera is made and things are
So, Mel, I guess that does not pertain to what we're doing right now. For example, if you
Okay.
have MRI images and you're going to put MRI images to predict something great, if you have, let's say, you're using face, for example, you have people with 100 people with depression, take their faces and you take people who are otherwise laughing and healthy, take their faces, maybe, right? But again, I think it may or may not work, but that is one, just to give you an idea. But we are not doing right now synthetic data. I think that we can leave it to the next session. Yeah. Thank you so much. We'll go back to some questions which we have from the chat. Dr. Raju Gopal sir has asked, will the ML model improve if we add more data or feed more ambiguous data with classical binary data? So if you try to make it more creative, does it work better or does it fail? Yeah, so I think what I try to say this, sir, is that the better like I think Shahir already said, garbage in, garbage out, the better data you put. Let's say you get the best radiologist and you get the best images, your model is going to be best. That's ultimately what it's going to be. Shahir, am I right?
Yeah, absolutely.
And feeding data, I think obviously the more the images you have, the better it is. The more you are actually giving it more chances of looking at complexity. So I'll give you an example. Shahir gave a lot of examples from our own training world. Let's say a radiologist, right? He is doing his residency. He's trained. He has seen about 100 MRI images, right? So he'll be good to an extent. But the same radiologist now, he's 10 years experience and he's seen 10,000 MRI images. Naturally, the person who has seen 10,000 has seen everything, right? And probably he is likely to be more likely to be better at making the diagnosis, right? So obviously, experience and number does matter. So that's the point. So I think more the merrier here, right? Yeah, sure.
And yeah, I had a very good experience with that kind of a problem. So we were creating an AI thing to predict the potassium levels. So we have this 3.5, 5.5 categories. So we were training models. So we were facing this conundrum. So AI model always got it wrong around the border. and a lot of patients were there near the border. Now, the question that was in our minds was, should we remove the borders and train the model so that remove some portion around the border so that model learns the actual signatures of hypokalemia, normokalemia, and hyperkalemia. But we may risk the thing that when faced with a border thing, it may never seen that and it may do anything there.
Right.
Versus the fact that we provide this ambiguous thing because the ECG would have been taken 4 hours before, but potassium level would have been taken later. So the potassium might have changed a little bit, and you are changing the ground truth based on that, and things can go haywire. So these problems we always sort by training both the models. So we remove the edge cases and we keep all the things, and we have an unbiased data set that we are going to face in the field where you can't have a luxury of dropping out the edge cases, and then see whichever does better. That's the one that goes out in production.
Good. Great. It's a great idea. Yes. Pallavi has asked, where can you learn about annotations? I think we're clear about annotation, Pallavi. The idea is that what we're talking about annotation is basically classifying you using your expertise or your radiologist using his or her expertise. Or for example, clinical images. For example, faces with Cushing's, right? Faces with acromegaly. So a trained endocrinologist eye will pick up acromegaly right when he's just waiting in the waiting room. Whereas somebody who's not, we will not be able to pick even if the patient is screaming acromegaly in front of them, right? So that's what happens. So I think annotation is basically using your expertise to classify the images. Sumanti has asked, if data size is less, is it advisable to augment the data? When you augment it with truth, so you augment it with good data, right? So the better data you put in, I think the better it works. This asked, and does sub-classification help? So like, for example, if you have different grades of acanthosis, so you have images of one with mild acanthosis, severe, does that make your model better necessarily?
It in fact works the other way around.
Yeah.
So what happens is if you have too many categories, then basically what happens is you are going more granular. The differences between each category reduce now. Say between mild, moderate, severe, and normal. If you go for this granular level versus say moderate to severe versus mild normal. So the differences between them are generally big, but when we make say instead of 4, we make it 5, then the borders start getting blurred. The features will start overlapping between the groups, and model will need more data to learn. It's not that it can't learn, it just needs that much more, and then it might reach a limit which may never cross because there is truly no distinction beyond a certain point.
Correct.
So if you're starting out as a research thing, I would always advise keep as much broad groups as possible and go with it. And as you gain confidence and data and cleaner data, and the fact that they are really different there, you should start like sub-classification from there on. But for the start, go for the broader groups.
Great. So cats and dogs, you start with that. I think that's a broadest group possible. And what you could do is start with the yes and no kind of thing. So if you're starting off in terms of research, presence of acanthosis or absent, right? That's the one which you're looking at to kind of generate. I think that's where you start with. And then once you get more experience, like Shahir said, collect more data, which is granular, maybe you could then look at that. Or you could do a structuring. Is it present or not? If it's present, then you make a separate model where you feed the data to the second model where you're trying to be more granular. Okay. Yeah, I think that's answered. Yes, a couple of things. Overfitting, is it like overtrained? A little bit like that, right? But it's like repeated training. So now what is happening is, from what I understand with overfitting, is that it only understands that the things which are given, it only takes that as truth. It doesn't look at the broader concept and broader picture. So that's kind of more like overfitting. It only exactly the type of image you are giving. If it shows only that type of image, then it will accept it. Otherwise, it will say that it's not. That could be a challenge. What about copyright issues? Anonymous attendees are. So I'll just say these are images which are freely available data sets. There is a site called Kaggle. We'll actually come to Kaggle, planning to do that today, but we'll do it next time. Kaggle is a free Kaggle. I think Shahir also showed you in one of the slides. So Kaggle is basically a free repository of data. So a lot of people have volunteered their own data. They want you to generate models out of it. It's freely available. Hopefully it's copyright issues like with them rather than us, but they've given it free, so you can try it out. And again, most of the Google images have different type of copyright settings, but most of the time there is Creative Commons use, so you can, or MIT license where you are actually allowed to use it. That's not a problem. If it's copyrighted, then probably it will not be freely available to you. So I think that's the thing. And you can always use it for training. Most of the ML people actually leached out information. All these big chat GPT, everything have leached out information from the internet without copyright. Someday it's going to get them back. We don't know that, but that's a area. Yeah, we'll just take a couple of questions and we'll finish it. I think we are a little bit, we are almost half an hour beyond time. So thank you all again for being here till so late. It's really interesting. AI is always interesting, Shahir. We always get people hanging on till the last bit. Yes. Yeah. Anirudh has asked, can we overcome it by developing better two models first, cat and exactly. So that's what I said. First, say whether it's cats or dog, and then you take the dogs and then make a second model where you classify the dogs. So that's the right way of doing it, right? And you can integrate. So we do a step-by-step process, right? So it's possible to do. Yeah. So this is actually what we did with Shire. We had actually quite a while back. We actually made a model. Again, we stumbled across Google Teachable Machine. We are planning to make something for the thyroid score. So we did exactly that. Instead of making the entire thyroids, we actually made it step by step where you look at different structures of thyroid, components of the thyroid score, and you actually calculate the score. So that worked very well. We actually presented that in the ATA conference, in the ITS conference in Kochi. Just last question. Hemant has said, Google has opened up some of the models for public use, radiology models. Shahir, are we competing with the big players when you're doing research? And this is, I think you answered this already, but just again, once again, it feels good to say that we're just scratching the surface. So you're still not late in the game. So can you just reiterate this point again?
Yep, absolutely. Think of it, right? Google has all the compute in the world. Google has all the engineers and all the machinery, everything. What they don't have is Indian patients who are willing to share their data with them. And
That's
that
right.
is available with you. And a lot of people have been very charitable in the medical ML field. They have outsourced their models for free. So Google has no great advantage over the architecture itself. If you think of DeepSeek versus ChatGPT, right? It already leveled the field there when it in fact gave it for free without charging a penny for it. So such kind of models exist, like you also mentioned, right? It's MedGemma that has come most
Right.
recently, open source thing. You can use it for free. Now you have data that they don't have, and there are not enough people thinking of all the problems in the world. So there are hundreds of thousands of problems that Google can never address because they can't focus their entire company towards medical science. So they have other problems to solve. They have space to solve. They have quantum computing to solve. They have thousands of problems. Number of people are less. So there will always exist an opportunity. And you should pick these small, easy wins, right? And start writing papers because that will become very common in next 5 years. After 5 years, everybody will be doing AI. Now is the twilight time when you have an advantage. Go for it. Do it. It's extremely simple. No rocket science. Not even simple 10 standard level science, really. So it is that easy. Go for it.
Absolutely. That's a great message. And I think end of the day, even if somebody has done that, research is you are redoing it, right? I'm sure 100% there are studies which, in fact, studies are done. Medical research is that are you able to replicate the study? You are always allowed to replicate. That is also research. So if somebody has already made a model for classifying diabetic retinopathy, you can make another one, right? There's no harm in that. Maybe your model is better. Who knows? Because you have probably better data set. So that's what ultimately happens. So you have more data set, which is conducive to your image quality and your type of patient. So I think, yeah. So that's it. Shahid, fantastic. I'll say great learning. And thank you for being part of it. And thank you for accepting this for this. It's always great to have people at some point of time. We all, and a lot of people here, a lot of us felt crazy that we are the only people who are doing this. Nobody's really interested. Until I met you, I think it said that I'm not the only one. Or for that matter, Avnish last time, it's like that you're not the only crazy people there. Yes, that
Feelings are mutual.
mutual. Yes. So we handed our back to USP, who have been very kind supporters of this. Again, complete academic freedom for us. Yeah, back to you.
Thank you. Thank you so much, Dr. Lakhani and Dr. Shahi sir, for bringing this to us. Thank you for the very explicit talk and lead that I'm sure that must have benefited all our participants. Looking forward to the next module. Thank you so much.
Thank you. So I'll just end by saying, Shahid, thank you once again. And module 3, we are having it next week, where we're going to take up a tool which is called Orange, where we're going to learn. A lot of people had these questions, the actual numerical data. How do you process that with machine learning? So we're going to take that up. We'll also see how we can use ChatGPT or some of these other tools also for doing that same. But I think that's what we're going to see. And we're going to have Dr. Atul Tiwari, who's a pathologist. He does this, again, like a lot of us, most of the time, apart from his regular clinical duties. Yes. So,
Thank you.
yeah.
Thank you.
So, thank you. And good night, everyone. And thank you for sticking around. And thank you, Shahid, once again. Good night.
Thank you. Bye.
Thank you. Thank you, team.